Good morning. My name is Weigang Wang, and I'm a associate professor here at the University of Arizona in physics and ECE. And today it's my great pleasure to introduce you this morning's keynote speaker, Dr. Raj Jammy from IMEC. Dr. Jammy is a long-time player in the field of semiconductors for over 25 years. He is currently the president of operation at IMEC USA. He served as CTO and the chief technologist at Mighty Ingenuity and the executive director of the Semiconductor Alliance. He led the effort at Mighty Ingenuity to develop a vision and operational plan for the National Semiconductor Technology Center and the National Advanced Packaging Manufacturing Program, coordinated with DoD microelectronic interest. From 2016 until recently, he was the global president of Semiconductor Process Control Solutions at Zeiss. Prior to joining Zeiss, Raj was the Senior Vice President, Semiconductor and Emerging Technology Business Unit at Intermolecule, a startup company with a combination of technology and the software engines. Raj served as the Vice President of Materials and Emerging Technology at Semitech, a global semiconductor industry consortium until 2013. At Semitech, he oversaw the consortium's effort in front-end CMOS logic, memory, and interconnect. And he got his PhD degree from ECE at Northwestern University. After that, he joined IBM, worked at the renowned IBM Semiconductor Research Center at T.J. Watson. He held more than 50 US patents and more than 225 publications. He has been co-chair organizers for many conferences, and right now he's sitting in many committees. For example, he's sitting on the executive steering committees for the IEEE Very Large Scale Integration Technology Journal. And he is also on the committee of NIST Industrial Advisory Board. Without further ado, let's welcome Dr. Raj Jammy.
Thank you again. Appreciate the introduction. Good morning, everyone. It's a pleasure to be here, and let me get this fired up. Okay, as it pops up here. Well, very good morning, and it's a pleasure to be here. Thank you for the organizers for inviting me here, Liesl, Zafar, and rest of the team. I want to also give a shout out to Connie for all the kind arrangements, Rebecca as well. And I mean, how can anyone refuse to come to Arizona at this time of the year, right? It's beautiful out there, and I truly enjoyed my visit. Just like Todd did yesterday, I also have to make a statement before I kick off my presentation that anything that I say here or express here is my personal views or IMEC's, not that of the NIST Industrial Advisory Committee, to which both of us belong, and both of us have been having very good and interesting discussions. Now, the theme of what I wanted to share with all of you today is collaboration, and why collaboration is such an important aspect that fuels the innovation in our industry. Without collaboration, honestly, we would not be where we are in the industry today. I'm sure all of you would agree with that. Now, of course, before I do that, I also must acknowledge a lot of colleagues. I am standing here in front of you making this presentation, but in reality, all what you're going to see is their hard work. the important thing to think about right now in my mind is we are in the limelight. We, meaning the semiconductor industry, is in the limelight. How often has that happened? In my 25 plus years of career, I'm super happy to see that for the first time there is so much attention. Are you getting an echo from this? No? Okay. I'm really happy to see that there is a tremendous attention to the semiconductor industry and all that we do. So this increased awareness of chips on one side has of course led to CHIPS Act and a whole range of opportunities within the CHIPS Act, NSTC, NAPMP, a whole range of manufacturing institutes and other things. But keeping that to the side, I think what is more important for all of us to remember and important to keep in our minds is the fact that our industry is global. In fact, I would say that our industry ecosystem is so intertwined that it is almost impossible to say that we can separate it out on a regional basis or on a local basis. So the CHIPS Acts that we have around the world aim for local resurgence, but many of them also have this tendency towards saying we want to onshore things. Yes, onshoring is important, and onshoring and resilient supply chains are very critical, but we also have to keep in mind that it is irreversibly global, and it is not easy to say that we can completely onshore everything. And why I say this is because I think while we see that the ecosystem is global, one very important thing that we need to keep in mind is that the clicker should work. The important thing to keep in mind is that as we have a lot of attention on all these CHIPS Acts, there are inflection points around us. The industry is changing for sure, but these inflection points are also opportunities. There are risks, serious risks, but opportunities that open up. First and foremost, as I was saying, the supply chain is irreversibly global. And the important piece is that if we do not coordinate this supply chain and the R&D that happens in this supply chain, then we would essentially be trying to do things that will duplicate and not necessarily help in what we need to do. You have to look at it globally, because while the different regions have kicked off these CHIPS Act activities, there is a huge risk that you are going to repeat and duplicate things in different parts of the world. And when you do not aggregate the few resources that you have at your disposal, you are going to end up repeating and not learning from mistakes. Because all we saw yesterday in the presentation that Todd was giving, as well as others were giving, is that learning is an exercise where you fail, and you fail fast. In fact, you learn a lot more from that. So if we are going to be repeating exactly those failures once more and not learning from what has happened, then we would be wasting our resources and energy. So I think it is extremely critical that allied nations and partners around allied worlds must coordinate and must work together to make these CHIPS Acts focus and vector towards common goals. Now, a little bit about who we are at IMEC. I'm sure many of you have seen IMEC. Some of you have visited us. But IMEC is very happy and proud to be celebrating its 40th anniversary this year. We started in 1984. I think there were 6 professors and students got together to start what was a small effort in the same buildings that you see here. But those buildings did not exist, though. It was a small little campus. Today, IMEC is 5,500 people strong. We have more than 600 companies and also about 500 researchers from those companies embedded on campus working in our programs. And we also have a number of students that have been part of IMEC programs and have been part of their thesis research at IMEC. We're very proud of that. And this exposure that students get has been valuable to them, but also has been extremely valuable to IMEC itself. So I would say that our budgets, in some sense, the infrastructure that we have, we must thank the European Union and the state of Flanders. Flanders is a small state in Belgium, but what is really remarkable is that they have been steadily supporting IMEC over the years, to the point where I would say that there are $3 billion to €3.5 billion euros worth of investment in CapEx that you see, the buildings that are over there. And more recently, as part of the European CHIPS Act and other engagements, they have announced another $2.5 billion worth of investments. 750 million coming from Flanders, 750 million coming from European Union, and additional monies coming from different partners. So this kind of investment is absolutely critical and necessary for keeping the actions and the research that we have been undertaking for a long time going. But we are also proud of the fact that 75% of our budgets come from the industry. And this is an important piece of who we are. But before I jump into showing you a small video, I think something else that might be very illustrative is over the years, the support from the state of Flanders has really kept IMEC going. And it has also been a good component, not necessarily the largest component, but a good component of who we are and how we've been able to make things work. Today, I would say that there are even new companies that are being created from IMEC research. About 120 or so companies have been spun out of IMEC, and we have a venture capital arm that also supports these companies. So IMEC has become a trusted partner after 40 plus years. We have literally become the global hub for nanotechnology and nanoelectronics. So we're really proud of that. And I want to share a small video with you that basically illustrates some of that.
Semiconductor technology roadmap by performing cutting-edge research on materials, device concepts, and process steps, and by making these innovations industry-ready. To develop technology that's years ahead of current manufacturing standards, IMEC offers its partners a 300mm clean room that contains more than 200 advanced tools and where more than 500 professionals work 24/7. The capabilities in IMEC's clean room include the world's most advanced patterning equipment and state-of-the-art etching, implant, cleaning, and deposition equipment from leading OEMs. In our Anno lab, we perform fundamental research into high numerical aperture EUV lithography. IMEC's 300.
Okay, that's good. That's all right, no worries. So moving on from there, I think we talked about revenues and budgets, and I just wanted to share this. Since 1984, you can see the steady support that the government has been providing us. And I think there is another chart where you'd see that as a proportion of the overall budgets, the industrial contributions are quite substantial, 75% or so. But in the beginning years, you can imagine it was definitely something that the government had to support, especially in the formative years. And today, the numbers have remained almost steady, if you can draw a line, just to give you a visual of what it might be. But we are really proud of the fact that industry has stepped in, and we are able to partner with a number of companies to make this all come together. I think this is 2022 numbers, but we are more like 920 million or so in the last year. Moving on, I think a very important aspect of where we are all headed comes from how innovation is being done now. In fact, I was having discussions yesterday with a few people in the audience. Innovation is no longer driven by what we used to be doing before, which is the core semiconductor technologies. It's absolutely critical that the core semiconductor technologies are still looked at. However, innovation is now vectored on these core semiconductor technologies, but it is mostly driven by technology platforms. It's also driven even more so by the systems and the system on a chip architectures. But all these are indirectly or directly driven by, I should say, the applications. So just to put that in context and perspective, in the past it used to be that we would make a chip and then say, okay, now application folks figure out what to do with it. And that was a totally different world. Today, it is the application teams that are saying, I need this chip or I need this performance in my chip. So how are you going to make that for me, chip maker or a package maker? Well, more so the package makers now. So this is a slightly different context. What this is really doing is it is putting a lot more pressure on how we integrate across the stack. And that is part of the decadal plan that Todd was also sharing yesterday. It is an extremely important thing that as you select a material or a design, you think through the entire stack all the way up to the system level application and usage, without which it would not be easy to drive or power the innovation that we are all interested in. And this is because I think the application workloads are being driven by perhaps 3 or 4 main thrusts. The GPUs for training, of course, ChatGPT and AI are in the news, but AV VR is also something else, or AR VR is also something else that is also catching up quite a bit, and this is going to drive a lot more loads in the near future. Autonomous driving for the past, I think, few years has been in the in the agenda, but how do you bring all these communication technologies, multi-sensor fusion, as well as real-time computing at the same time to happen? I mean, there is no rebooting on the road. So there's just a lot of work that needs to still happen, but these are all the different thrust vectors that we need to keep in mind. While this is happening, I think the problem that we are all running into is the fact that in the past, we were used to this 2x improvement in performance to train, but that's no longer the case. And we, over the past 3-4 years, I think, or I should say maybe over the past 7-8 years, we are used to something even faster than that, more like 50% for training our engines, and there is approximately from 2 years time frame, it went up to 6 months time frame, or doubling in 6 months. I think it is plateaued out now, and that plateauing out is actually going to cause a lot more problems right when we need help with all these training models that have to grow. Now, if you move forward and then look at what is happening to single-thread performance, a number of chips today, of course, are multi-thread, but just for a minute, if you look at the single-thread performance, that is actually flattening out. It's no longer the 50% growth that we used to see. It's about 5%. And at the same time, the cost of chip design is going through the roof. So these are really basic challenges that we need to keep in mind. And then on top of that, you have the interconnect bandwidth, which is not really keeping pace with compute power that is increasing. While the compute power itself is not so great, and we're not very thrilled with it, interconnect is lagging behind even more. So we have to figure out how do we transport this information, and the growth there is 1.4x improvement in 2 years versus what's happening with chips, which is running at about 3x for every 2 years. So, SRAM is one of the core components, as many of you know, for any logic chip, but SRAM bit cell dimensions are also very relaxed and getting even worse. But the scaling has completely slowed down, in fact, to the point where it is flattened today. So you have to have something completely different, or a different architecture, or a different concept for SRAMs. And there is no real silver bullet out there yet, although everybody has been working on it for a long time. And then, of course, the power wall. This whole 100 watt per centimeter squared power wall that we've been living with for nearly a decade, or maybe even more than a decade. If I look at this chart, I think it is since 2005. So maybe we're hitting into the second decade of this. We haven't really surpassed this. We haven't really tamed this beast, and we do need to do that fairly quickly. So with all that background, I think the things to keep in mind are, I'm not trying to come here early in the morning and give you a doomsday scenario, but what I'm trying to do is to say that while it looks very glum and it looks very troubling, I want all of you to look at it in a positive way. That's where job security comes in, because all of us still have good things to do ahead of us, right? And the industry is going to continue to scale, and what you'll see is that there are multiple technology themes that are going to power what is happening. Density scaling will still be needed. We will still be looking at density scaling. New devices and new device architectures, new device concepts are going to be absolutely critical. We saw a lot of discussion around 2D materials, 1D materials yesterday, and as well as other technologies. And then you have all these connectivity issues, which is whether it is between systems or within the system or even system to system, all these connectivity issues are going to be dominating too. So as we do this, the system technology co-optimization is still going to be very dominant and very important, which is what we saw earlier in one of the charts that I had shown. The second part of it is that form factor, cost, and sustainability are going to be very critical too. So we can't ignore these factors as we try to scale. Now, I want to give you a few examples of what we are trying to do at IMEC in this regard. Bear with me, some of these are a little slow in terms of videos, but this is the standard gate all-around transistor that everybody is used to, and we are trying to, everybody's trying to commercialize this. So one embodiment of this is the nanosheet transistor. Especially as you go towards 2 nanometers, I think nanosheet will become more of the common architecture across the industry. Now, these nanosheets, as you can see over here, the horizontal sheets that you have over there, are good but not good enough. So at IMEC, we came up with something called a fork sheet. And what we do here in this fork sheet is you bring these nanosheets, the N and the P, closer. And so therefore, you're able to scale better. And you gain about 10% performance advantage, and you gain in terms of area for SRAM bit cell about 30% or so. So that's an innovation. that came from IMEC team. Now, while this is good, we feel that as we did our modeling and as we did our simulations, we realized that this alone is not enough, and we need to do something even more than this one. So one of the reasons why we need to do more is, as you see the dimensions around some of these nanosheets, you notice that especially for the thick oxide devices, the I/O, you don't really have any room to do work function control or to do the NFET and PFET demonstration. So you're running out. Once you put the oxides, you're running out, and you have to put these nanosheets close so that the RC constant is not going through the roof. So we came up with a different option, which the industry has been talking about as well, which is called a complementary FET. So the fork sheet literally translates to what we call the CFET now, where you take the NFET and PFET and you put them one on top of the other. Right? So by doing this one, you gain quite a bit in terms of area scaling, but you also gain in terms of performance, but you add complexity. Process complexity is just huge. You also start thinking, okay, now how am I going to wire all this? It was bad enough to wire things when they were flat, or not flat, but at least something like flat. Now you're trying to put them one on top of the other, which makes it extremely complicated. And that's, again, good job security for everyone. But that's also an opportunity for new tooling. It's an opportunity for new technology development. And there is a lot of exciting work that is taking place in this case. Now, one other interesting innovation that is happening is backside power distribution. And I want to touch upon this because in the past, when you supplied power, it was literally percolating through all these 16 layers of metal from top to the bottom, and the device that needed the power was all the way at the bottom. This is not the most efficient way, because now you're dealing with entire losses or the losses that come in from RC and everything else in between. Now, what the industry is doing now is moving away from this one, and you're now looking at backside power distribution, where literally you're minimizing the number of metal layers that you need at the top, but you're providing the power from the bottom, as you see in this picture over here. Now, this is opening up a lot more opportunities, and you'll see why I'm saying that in a short while. But implementation of this is already in full swing, and in companies like Intel and others have announced that they would be making backside power distribution a reality very soon in one of their new products. And what you see here is an example of some of the work that we have been doing at IMEC to understand exactly what processes need to be honed, what needs to be improved, where it doesn't work, where are the cliffs, process cliffs, and other things. You're seeing some nano TSVs here. You're also seeing some of the fins in the middle. There's a 4-fin device, and how the backside metal, essentially this is a buried power rail that you're trying to connect through. So this is across a TEM cross section, but this helps us to look into what might be the future roadmap. And going from nanosheets to fork sheets to CFETs in future, I think by the time that gets implemented, it's probably more like the 5 or A5 generation, and the nanosheets are coming in at about 2 nanometer generation. But with each of these, you see the improvement in the area. When you go towards nanosheets, a 6T cell is possible, but by the time you bring it to fork sheets and to CFETs, you're going into a 5T SRAM cell and a 4T SRAM cell. So there is a significant advantage in terms of its area scaling. Now, something else that is interesting and important is the back end of line scaling. This is not moving as fast. This is not moving as attractively, but so we need to do something radical here. I don't have any clean solutions. But what you're seeing is subtractive metal. Essentially, we're doing dual damascene for a long time, but we have to start thinking about putting in things like ruthenium directly and have self-aligned contacts, and perhaps in the longer run, even more exotic things like graphene layers that might help, or maybe even other alternate replacements for copper. But this is yet to be demonstrated. So with all these challenges, with all these complexities that you see over here, is there really an alternative to how we do CMOS? And that is something that we need to contemplate, and we've been chewing on. And what we think is, if we start looking at SRAM scaling, if we start looking at how do we deal with IOs and power delivery, high performance versus the low power, and also the workloads, it becomes obvious that we need to start thinking of a different flow or a different flavor of CMOS. We're calling it CMOS 2.0. No imagination there for us, but it's not very imaginative. But CMOS 2.0 is where we come up with, where we can optimize the SOC We can also optimize how we do the 3D part of it, because the packaging and chiplets has become very important, backside power delivery, as well as the interposer itself, how to make it active interposer. So what you're looking at here is an SRAM layer at the top, which is basically the cache at the end, and then there is an active SRAM below that. And you have a driver logic, and then you have the dense logic, which is where much of the compute happens, and then there is a functional backside, which is the power delivery we talked about a little while before, and an I/O now on an active interposer, right? So these are all different pieces that are heterogeneous now, but we start thinking about how do we bring these things together, because the SRAM at the top could be an alternate memory technology, and some memory technologies are showing signs of that. Now the drive logic could be done in a legacy node, and you don't have to really keep the dense logic. You don't have to do it at the same time and mix it up in a way where you're constrained because of the fabrication processes, but the most advanced node with low C, the low capacitance in VDD can now be implemented with a totally different dimensional freedom. And then you have the I/O, which can be done on legacy nodes as well, and that's done on an interposer. Now, if you start bringing all this together, right, with hybrid bonding or wafer backside processing and even micro bumps wherever they're appropriate, you have a very different context of how a chip comes together. So this is of course not done. This is the concept, but this is the direction that we need to go, and we believe that this is what is going to fuel what we all have to do in the future. Now this also helps us with the STCO options, because each of these layers can be independently tuned based on the application that you're going to deal with. And each of these layers can be micro bumped, or you could be hybrid bonding based on the complexity and based on how these technologies have to come together, again driven by application. Excuse me. If I'll skip this in the interest of time, but as I said, this is not done. There's still a lot of work to be done here: cost, yield, the interconnect density and scaling, EDA tools, and how do we deal with EDA tools that can connect back and forth between these different technologies, as well as the thermal challenges that go with them. So at the same time, the packaging side, as you all know, is also modulating quite rapidly. Chiplets are the hot thing today, and you're seeing a lot of partitioning around chiplets and 3D SoC actually disaggregating and aggregating back again on interposers. So scaling that technology also becomes extremely crucial and critical. So we are looking into hybrid bonding, wafer to wafer, as well as die to wafer, backside power delivery, how all these things come through, as well as delivery network itself for packaging technologies. So there's tremendous amount of work that is taking place at IMEC as well as at many companies. And what you see in those bubbles are already in production, and some of them are being extended along those lines. Now, I talked about memory and I talked about SRAM. So I just wanted to give you an example of some of the SRAM replacement options that we're looking into for cache. This is a comparison of different types of memory technologies: SRAM with STT-MRAM as well as SOT-MRAM. And I'm sure Wei Gang and Sohail and others are all very interested in this because they're also looking into some of these technologies. But what is important here is to see that SRAM is actually a dominant memory for a reason. We have been using it, and despite the pain, we've been scaling it. But we do need something new, and we think magnetic memories are potentially very strong in this space, and they also have other attributes. But it might be necessary to move away from standard STT-MRAM and move towards SOT-MRAM. It is a technology, it has some attractive features, it is a technology we've been looking into, but conventional SOT MRAM suffers from a lot of dimensional wastage, and we've been optimizing those dimensions to see how we can make it flip more easily when we need to, or write and read more easily essentially, and prevent some wasted current as well as wiser voltage usage, I should say. But there are still problems. As you can see, there is a single SOT driving multiple devices, and we have to figure out how do we address each of these devices separately and independently. So there are still some technical challenges that need to be looked into. Now, on moving on from memory, the big problem has been moving data in our field. I think Todd was also alluding to this yesterday. This is really where the bottleneck is, because we generate tons of data, we store it, we bring it back for processing, and then we take it back again. So this process is literally killing us And since we are not scaling interconnects, but moving a lot of data, we have to start thinking more outside the electron confinement box. We have to start thinking of using light. And what you see here is a chart that helps us understand how integrated photonics and optics can enable future systems. We would love to replace electrons with photons yesterday, but there are still a lot of challenges in trying to produce light on chip, transport it, or transport that light and the signal to some other chip, and then again reconvert it. It's not easy, but it is already happening in the communication sector, and you will see that it is moving slowly into where we need to be. Maybe it's better to explain it using this chart, where you can see that on the long haul there is a lot of usage of this. Even rack to rack, I think there's a lot of optics and photonic components that have come in. At IMEC, we're looking into how do we keep those technologies moving and how do we extend those technologies, but also we're looking into how do we move it into more integrated, I would say, pluggable, but more on-chip and co-packaged photonic solutions. And there is activity moving in all these different technologies along the length scale or the distance scale of where photonics could be applied. Some examples of some of the technologies that IMEC team has developed, you can see over here. We call it integrated silicon photonics platform. We have 200 and 300 millimeter capabilities, and this is something that we have been making available for a number of partners to use, exercise, not just for these kind of data transport applications, but also for a number of other applications in the life sciences field as well as sensing field and a whole range of other areas. I think this is one of the legacy areas. 22 years of research. We have more than 145 masks that have been taped out. Not some of them for us, but some for our partners as well. And more than 10,000 cumulative 200 millimeter wafer starts have been run till 2021. A lot of the work is now moving into 300 millimeters as well, and we've also started looking at integrating them with light sources and transport. It would be bad if I don't touch on something extremely important, so I decided to insert a few slides on what we are doing to the planet. As Todd was saying yesterday, the 3 Ps, the very important last P is the planet. As you can see, worldwide, we are producing 36 billion tons per year of CO2 emissions. Of course, if you fast forward and then look at what happens from the ICT industry or from the semiconductor manufacturing side, it reduces to about 100 million tons per year, but it's 1 ton more than what we really need. I mean, these things are just simply not acceptable, and we have to see how we can reduce our carbon footprint in the industry. So there is a huge team that is looking into many of the solutions that are necessary here, but we started modeling and asking ourselves, what would happen if we look at scope 1, scope 2 technologies as well as the greenhouse gas emission in chip manufacturing. And what you see here is if you do nothing and if you just continue to do what we do today, we will be 8x away by 2030 from where we need to be. So that's only going to make the problem worse, assuming that this is capturing to some extent that the industry is growing, but not necessarily the rate of growth with AI and other technologies that have come in. So it probably will be worse than this. Now, if we look at some of these growth rates and then say, okay, we are going to indeed look at renewable energy and try to do some greenhouse gas abatement, there is some hope that we would be at about 2.5x better, or 2.5x worse, not 8x worse. So it's better, but not necessarily a complete solution. So this is something that requires a very urgent attention. And I think as we develop new technologies, as we develop new solutions, it is super critical that we look at the greenhouse gas as well as the CO2 footprint impact on any new technology, any new tooling, any new concepts that we bring to life. And again, that's where I'm actually quite excited about some of the photonic solutions, because that starts helping us. In addition to that, it is very important to keep in mind that future computing is heterogeneous. That means it's not just one CMOS-like solution that is going to solve all the problems. We would have to figure out how to bring different computing platforms together. Some of them could be superconducting computing platforms, or some of them could be 2D based, and some of them could be completely different, and I don't even know what they would be, but we would have to potentially use each of those technologies for specific cases. So keeping that in mind and keeping the fact that we do need to do something about our carbon footprint is a very critical paradigm to keep in mind. Now, bringing all this together, I thought you might be feeling very sleepy by now. So I figured I'll bring an eye chart in front of you. Now, these are the programs that we're running at IMEC. I didn't touch upon some of the technologies that we do, but what I wanted to share with you is that the core of our activities are focused around this green box that you see here, the highlight. The compute technologies, the storage, the connects, how do you connect different pieces, the sense and actuate, as well as the power. And I didn't get into sense, actuate, power, or some of the connect technologies. These are all driven through GaN, as well as indium phosphide and a whole range of other technologies on silicon. But these core technologies are now also encompassing what we call the SSTS program, which is the sustainability activities that I just shared with you. The DTCO, STCO activities are also embedded into that, because you do need to have all these researchers have a dialogue around this. And I think sooner than later this will start extending to the right, where you have the sense, actuate, as well as the power components coming in. Now, this work is not done in isolation. It is anchored on fundamental process materials evaluations and process technology development, which forms the bedrock of what we do. And our partnership with ASML has really helped us in patterning technologies, and of course now CMP and Etch are also patterning technologies, and so there is a lot of work that is going on with suppliers from that community as well. In addition to that, we never forget the fact that applications are driving everything. So there is an extensive partnership that is happening also with application drivers in the system makers, the life sciences sector, and a whole range of other areas, automotive and energy sectors as well. So this we try to, I won't say that we are always successful, but we try to bring the connectivity that is necessary between all these different sectors and different components to ensure that we are moving in the right direction. And we get a lot of input, and we get a lot of valuable input, I should say, because of our partners. The collaboration that we have is the key to make all this come together. So we don't necessarily make product. What we really do is help people make product. We take ideas and innovation that are either coming from universities like yourselves here, or from other locations, maybe some invented or discovered by us, and we translate them into something that is more industrially friendly, and it gets into facilities and fabs around the world. Many times those solutions are actually solutions that don't work, and that's where there's money, because you know what not to do, and you can just focus on what needs to be done. But as we do this, we also count on the partnership with materials and equipment suppliers and EDA suppliers and others, because that is the medium in which you have to make these solutions work. And we supply that to startup companies, and we work with other innovative newcomers who will take advantage of this and move the technologies forward. Now, this is sort of a cycle. That's how the technology moves. But one thing that we discovered fairly early was that if you do it in a sequential model, where you say, I am going to take the materials supplier's solution and then evaluate that and then put it into a tool and then take it from the tool and put it into an IDM, that whole process flow is very slow. This is what a traditional model is. One thing that has, I think, been very advantageous with IMEC is that we have actually combined all these players. We brought them to the same place. We helped them work together with each other, and this speeds up innovation. And we've really benefited from this networked innovation model over the years, to the point where what we see today is in this approach, we have a lot of embedded partners from all the research companies, but in the ecosystem itself, we have attracted all the IDMs and foundries, but we've also attracted a lot of companies that are moving into more non-traditional space, like the power or automotive suppliers. But we also count all the equipment suppliers, the system makers, essentially the equipment suppliers, as well as the material suppliers, and increasingly more system partners from non-fabless side. I mean, the fabless companies, some of them are systems and some of them are not. But what we see is that a lot more system partners are coming into membership and partnership. So this has really been very valuable for us, because when you collaborate, when you listen to the ecosystem, that's when you can also figure out where to go and where not to go. So we've been benefiting from this partnerships quite extensively. Of course, what does this all mean for here in the US, and what are we doing here? I am from IMEC US, and so I wanted to share with you where we are in the US and what we're doing. So in the US, we have offices around the country, and more offices might be open in the near future. But one of our earlier partnerships was with Bridge in Florida, where we have a design team and also some actual physical work that happens in the Bridge facility, where we transfer some of our packaging solutions. Today we do some specialty packaging activity there, but we also work with some of our superconducting devices, and we are also doing RF technology development over there. We have 2 units that are on both sides of the coast. One is in California and the other one is in the Boston area, which is called IC-Link, and they provide a lot of design support, all the way from MPW runs to custom design for a number of companies, and actually more universities and national labs. More recently, we have announced a partnership with Purdue, where we're doing a lot of materials and modeling with Purdue faculty, and we are also working with University of Michigan. This has just been announced, where we focused on automotive technologies and automotive technology development. Just a quick plug-in for our team in IC-Link. This is a team that has been supporting North America for more than 5 years, and we also take advantage of what Europe has called Europractice, where a number of facilities or a number of universities and national labs in Europe have come together to establish what this Europractice, where the design services are orchestrated and coordinated so that people who don't really know how to optimize something for an MPW run can just go to Europractice and get it done much more efficiently. In that way, when those parts go to a TSMC or an Intel or Global Foundries, they have much better chance of success. But IC-Link has been working very closely with many companies and foundries in the US, and we've helped more than 300 companies, 700 institutes. I think even for Sandia National Labs, we taped out a 7 nanometer FinFET a couple of years back. So this is an effort. But how does this all fit into the context of collaboration, and what do we need to do? So I thought I'll switch tracks here a little bit and talk more about what is happening in the US and what we need to do here. If I look at the US map, I would say that semiconductor strengths are distributed across the country. And what you're seeing here are pockets of strength in traditional as well as non-traditional semiconductors. But how do we bring all these capabilities together, and how does that come together in the context of the CHIPS Act? I think before we do that, maybe a pause to look at market dynamics, and then we can dive into asking ourselves some of these questions. Market dynamics wise, US still is the largest revenue driver in the semi industry, period. We don't make as many semiconductor parts as we used to, which we should, because that ensures our security as a nation, but we still control much of the revenue, right? Now, the industry is supposed to be going to $1 trillion in the near future, and I think a good significant chunk of that will still be managed and controlled by the US. We are really strong in fabless, and the fabless sector is growing. We are also strong in equipment and EDA. But what we are trying to do now is we are trying to spend nearly $11 billion in research. Even if you assume that a good portion of that is going for CapEx, you're still going to be spending about $1 billion in R&D per year over the next 5 years or 6 years or 7 years roughly. So I just showed you a little while back that in the pre-competitive R&D space, IMEC's budget is approximately $1 billion. We are adding another $1 billion into the system. So the question that I want to pose to all of you is, what more are we going to do with those $1 billion? How can we collectively do something that is accretive, not duplicative? It's absolutely critical that we think about this very carefully. And therefore, it is very, very critical that we pool resources and we pool the problem set and define what are we going to do together as we move forward. The US CHIPS Act, it can accelerate this technology differentiation for all of us in the allied world. Or, we could just be we could just be wasting resources, because we need supply chain resilience. And if you're not going to get supply chain resilience if we do the same thing in different parts of the world and say, I am going to try to encourage my own national or regional partnerships, and I'm going to work in that region. It may be successful for some time, for a small period of time, but I bet you that it is going to increase the risk. Because if something goes wrong, you really don't have anywhere else to go. And therefore, it is important that we have no one-of-a-kind solutions or one-of-a-kind supplier situations. And I think the CHIPS Acts, not only in US, but in Europe and other parts, can be very transformational for the allied world. And that's what we need to be focusing on, and that's what we need to be aiming towards. Now, I want to jump ahead to what the Commerce Department has released in terms of what they want to do. The CHIPS Act plans to have a number of technology centers around the country so that the problem can be distributed around the country. It's a national problem, and we need a national solution, no question about that. But in these different technology centers, how are we going to coordinate these different problems that we are going to deal with? Are we going to silo each of these things and then say, I am working on power electronics, and I am not going to worry about what my power electronics require or do in response to, let's say, how I integrate that with CMOS, or how I integrate that with IoT. That's not a winning formula. That's not a winning formula. You have to think about how do we get system-wide coordination, and how do we address these gaps, and how do we ensure that there are grand challenges which actually force people to work between these different technology centers and rely on each other for solutions. Without doing that, we will not really get to achieve the objectives of the CHIPS Act. In fact, if I look at what might be a biggest gap in the US right now, it is the availability of test vehicles, baseline platforms, or baseline platform flows that are going to drive coherence. My vision and my hope is that somebody from University of Arizona wants to do something in MEMS, and it is running out in, I'm just making up something, MIT, and you're able to just simply say, okay, I'm going to access the next possible lot, I'm going to program that from here, and somebody over there runs it because it's a national capability. And similarly, somebody from MIT wants to run something here in the School of Optics, and there's a flow in photonics flow that they want to access here in University of Arizona. They're able to do it here because it is running over here, or it's running in a facility that is allied to each of these institutes. This way, you're able to aggregate data, and you're also able to aggregate the results and look at it with a much bigger database. And I say that with the intent of a digital twin behind. A digital twin is nothing but data, formatted data. So you need to define standards so that the data is all in the same standard, and then you have to eventually put it together, aggregate it for a digital twin. So this kind of common test vehicles, common program management, and common capabilities are going to drive coherence, and they're going to propel us in the right direction. And to do this, we already have a lot of capability on the ground. If you look at this pipeline, the way I see is innovation goes through a number of steps. As it goes from low TRL to high TRL, ideas could come from anywhere, universities, national labs, or they could come from startups. As they go through these ideas, as they go through this pipeline, initially you're really more focused on proof of concept. You want to make sure that a device wiggles, and that device is good, proving what you said you're going to do. Then comes the question of, do I have all the tools, and do I have all the capabilities, and how do I make sure that this technology is working the way it's supposed to work for commercialization? So that's where you need to bring in R&D fabs. Once those fabs are in place, then the question pops up, well, how is this manufacturable? I need to make this more manufacturing friendly. So that's when you need to start getting into prototyping. How do you prototype a test site? And prototyping is not in the early stages. Prototyping is more of a late stage game, but it is not a product. You are proving a test site that gives you confidence, that it is reliable and it has the right characteristics for my design. And it may be, I might be coming from a specific company, but somebody else coming from a different company may use a different version of it. So at the prototyping stage, you're not really focused on the product, but you're focused on the attributes of the technology. Because then in the last stage, as you see those pipes jutting out in the end, each company may actually customize it for their own product. And you have to give room for that kind of customization down the road. So there are stages, and there are capabilities and fabs that are already in the country that actually can help with this. This is not a one fab or a one size fits all solution. It can never be, given the complexity of what we do. Now, in the initial stages, you need flexible facilities. In the next stage, you need the capability to essentially have industrial relevance for the solutions that you make. Do I have the right design tools? Do I have the right 300 millimeter or 200 millimeter tool set where I can practice this and demonstrate this? Once I pass this checklist, now I want to make a prototype because it's more manufacturing friendly or more manufacturing relevant, and I want to check reliability. I want to see any failures that I didn't know before. And then comes transfer to high volume manufacturing eventually. So these are the different stages that we have to keep in mind, and each stage has its own requirements in terms of fabs and facilities. Of course, the first stage is mostly university driven. I would say IMEC is in the second stage largely. When it comes to manufacturing relevance, you have to work more closely with foundries, or at least foundry platform technologies, and use those technologies in facilities like IMEC or New York, Albany Nanotech, or other facilities which are more geared towards these kind of capabilities. And of course, HVM is purely done by the companies. Now, to make all this happen, as we move forward in the US, I think it is important to keep in mind that we need the device technology capabilities, we need the packaging technology, and the design technology. All these three have to come together. And each one has its own requirements, its own test structures, baselines, and a whole range of things I have listed out here, but I'm going to jump ahead in the interest of time. I personally feel that it is important to bring these together because any work you do in prototyping is eventually going to drive the applications and the systems that we are interested in. So it's a virtuous cycle, and to keep this virtuous cycle fueled, you have to drive in a coordinated fashion. This coordination and this collaboration is extremely critical, but it's also important that that collaboration is incorporating workforce development as part of it. We can't have workforce development separate. It can't be a separate program. It can't be something that is being done for the sake of workforce development. That has no relevance. You need to put those researchers, those students, those postdocs, and the faculty together along with the industry players. It doesn't necessarily mean that you need to have all universities have 300 millimeter tools. It's unimaginable and it's impractical because you cannot maintain a 300 millimeter tool and the cost of it would be wasted. But having access to that so that when the right time comes, students can go learn how those tools run, operate, how those flows are made is absolutely critical. That's why in my view, this whole workforce development is something that is encompassing all these activities, and we have to bring all these together. So with that, what I want to say is I've bored you enough, but if we want to go far, I think we all need to go together. Thank you.
Well, thank you so much for a wonderful talk.
Thank you.
And what caught my eyes is your $11 billion investment in R&D. Is that something's going to be internal, or is going to be outsourced, you know, for academia, industry? Do you have any information about that, or not yet?
Sure. The $11 billion is the investment that the Department of Commerce has announced for research and development in the US. Right. So I'm sure you're following all the action coming from NSTC. So that's part of the $11 billion.
Hi, a very
Mike.
quick question. You mentioned that your cryo efforts in Florida. As a university, can we use your manufacturing capability to fabricate some JJ-based superconducting?
Let's talk. Let's talk. I'd be happy to discuss. Yeah, we do have some capabilities that are running out of Leuven right now. But yes, we definitely can talk about that. Yes.
Raj, thank you. That great talk.
Thank you, Mike.
One point I want to make on your last quote here. The challenge, I think, for us being successful is not necessarily technology. I think it's a handicap with our business models. Everyone wants to go far, and they're happy to go together as long as they get the biggest piece of the pie and control the game. Yeah. So there's a real challenge, and I'm not asking you to give me the answer or solve it, but I just want to bring that up. We all need to be cognizant of that, and making value propositions to our companies and organizations that there's more in the whole than the sum of the parts kind of thing.
Now, it's a very good point that you raise, and I have had the pleasure of working at Sematech as well, and now with IMEC, and have worked extensively with SRC and other consortia around the world. One thing that I can say is, you're correct. Every company has its own interests, and that is the way it should be, right? But what is important in collaboration and collective work as we do is how much of that is pre-competitive and how far do we take it. At a certain point in time, that's why I try to illustrate that end of the pipe, this pipeline with individual pipelines. It breaks into individuals. For example, what you want at Raytheon may not be the same thing that Gil wants at Intel. But the core technology of, I don't know, I'm just going to make up something, how I put GaN on silicon and what processes work or don't work might be relevant for you for a different application and might be very different for Intel. Right? So how you commercialize that and what stage you commercialize that depends upon your needs. But much of the pre-competitive work can be done with pooled resources and in a collective fashion. So that helps us to send a signal to the industry suppliers because they know where to pool their resources and develop solutions that are useful for everyone. And they're also ready to react when you need them. Perhaps Intel is ahead of Raytheon for something there, and when you need it, maybe a couple of years down the road, they're ready to answer your needs in a more proactive fashion. But it's a good question, good point. This is something that vexes everyone in the industry. But what we have seen here at IMEC, what SRC has seen, or what we saw at Sematech before, there is a lot of room for pre-competitive work. I mean, EUV would not be here. I don't have to say any more. So.
Raj, thank you very much for the very inspiring talk. I have a question actually for students. I had a student who actually did an intern with IMEC, but he had to go to Belgium, So my question is like, in terms of opportunity in the US, I mean, are there any opportunity for internship for the US side for IMEC?
We hopefully, I mean, that is what, as we are expanding our footprint in the US, I'm sure that there would be opportunities opening up for students in the US. But if you really want exposure to the 300 millimeter fab or the 200 millimeter fabs that we have there, and the 5,000 people that are sitting in Belgium, you have to go to Belgium for some time. Perhaps in the future, maybe there is opportunity with NSTC as it's ramping up facilities and capabilities here as well. But collectively between the two places, if we are taking the big problem that we have in front of us in all these technology areas and splitting it up based on what the topic is, maybe students can go where they need to go and get that right experience. So it's a great opportunity in future for students, for sure.
Thank you. Any other question?
We have time for one more?
Oh, yes, please.
Okay. Hey, Raj. Wonderful perspective. Thank you. On the CMOS 2.0 strategy, you didn't really spend a lot of time talking about measurement, known good die, and assembling that structure. Can you comment on the magnitude of that challenge and where some initial investments might be made to help tackle that known good die problem?
Right.
Thanks.
It's a great question, Todd. I think the challenge with the known good die is for long. It now becomes critical because we are going towards chiplets, and you make a component. In fact, I think somebody from Intel had once made this comment to me. They said, we make these $1,000 parts that we send, and it's hinged on this $1 component that we are getting from somebody else in the package, and we can't. We think it's good because we've gone through our quality checks, but still, things sneak through, and our parts get wasted, and our reputation gets toasted. So it is a big problem in the industry, and I think from a metrology perspective, and Marla is doing a great job, there is a whole range of work that needs to be done. And I call this metrology because I was discussing this with someone yesterday. In our field, we have to look at things very differently now, henceforth. So far, we've had metrology that focuses on physical attributes, TEMs, SEMs, and how is the physics looking. Then we've had metrology that looks at chemical composition. And then eventually we would do electrical testing, parametric testing or reliability testing and other things. But I'm willing to bet that if the picture looks ugly, stoichiometry is not where it's supposed to be, but the component passes reliability and it meets all the spec, we'll ship it. So what I'm saying is electrical matters more than anything else. And when it comes to known good die, it is the electrical component that matters more than anything else. So we do need to come up with non-contact, non-destructive techniques that are going to tell us where that part is and how does it look in terms of its longevity for reliability. So we haven't really touched that. We haven't really come up with the right solutions that are going to help us with that whole game. Some of it starts at design, some of it starts at periodic non-contact measurements that have to happen through the process flow that give us assurance that yes, this is looking good. And maybe it's a built-in self-test approach or other things that still need to be codified. And again, standardization is important here. Otherwise, we'll be going helter-skelter. But it's a good question. Thank you.
Okay, yeah, please. We have one last question.
Thank you, Raj. This is Kashyap from SRC. So you said with $1 additional billion from the government, one place is probably where we can, bring the world to closer, right, with digital twins and stuff. What if we don't get 1 billion from the government? How do you think we can still achieve that, if that's the goal?
Right. So I want to be very clear, Kashyap. I'm not saying that we're going to get 1 billion from the government. The government plans to spend approximately $1 billion, right? That's what the CHIPS Act is saying in the US. And if you look at it, the European CHIPS Act also wants to spend some money. And then there are CHIPS Acts around the world. There's one in Japan, there's another one coming out of Korea, there's another one that has been proposed in India, a whole range of places. My question is much more rhetorical. All these different countries that want supply chain resilience, that want R&D, and that they want to be a player in this industry because of national and economic security reasons. If we all try to do this by ourselves, it's not a winning proposition. If the future is so heterogeneous, whether it's chiplets or whether it is even the computing platforms, then the problem set is actually much, much larger, right? Therefore, we have to divide and conquer. So if each of us can rely on each other, we focus on some aspects of what we can do, but have access to these capabilities in a pre-competitive fashion to a certain point, then it comes to how industry runs it from there. That's industrial policy that depends upon each country. That pre-competitive space where this $1 billion is planned to be spent from the US side, Europe wants to spend its own money, that's where I think we need to come together and we need to spend it wisely so that we don't duplicate. Some level of overlap is good because that gives you assurance, but not, large-scale overlap and repetition. I think that's just wasted.
Okay. All right. Thank you.
All right. Let's thank Dr. Raj Jammy one more time.
Thank you again.